When we gaze at the starry sky, the universe seems full of galaxies, planets, and shining stars. Yet, most of the universe consists of vast empty spaces where matter is nearly absent. These regions, known as voids, resemble wastelands in the cosmic expanse, holding the keys to unraveling some of the biggest questions about the origin and structure of the universe. Voids are one of the most fascinating and mysterious concepts in cosmology, showcasing the remarkable asymmetry in how matter is distributed on a large scale. While galactic filaments, galaxy clusters, and superclusters are regions of dense matter concentration, voids, nearly empty expanses of space, symbolize emptiness, where matter exists in minimal amounts. Their existence raises profound questions about the formation and structure of the universe. Voids, or empty regions of space, are vast areas in the universe with extremely low matter density, much lower than in other regions. If galactic filaments are the backbone of the universe, then voids are the enormous gaps between these backbones. These regions contain little more than small amounts of ionized gas and a few sparse galaxies, which are usually simple in structure and small compared to large galaxy clusters. Despite occupying most of the universe's volume, voids contribute very little mass, making them the emptiest areas in the cosmos. The discovery of voids marked a significant milestone in cosmology. They were first identified in the 1980s when astronomers used data from large-scale galaxy surveys to study the distribution of matter in the universe. Analysis revealed that galaxies are not evenly distributed throughout space, but instead cluster into groups, filaments, and superclusters, forming a complex network. Between these structures are vast, nearly empty regions known as voids. This discovery revolutionized our understanding of the universe's structure, proving that space is not uniform, but instead organized into regions of concentration and sparsity. A unique feature of voids is that while they appear empty, they are not entirely devoid of matter. Modern telescopes have detected small amounts of ionized gas within them, enough to produce faint signals in optical and radio observations. However, compared to dense regions like galaxy clusters, the matter density in voids is 10 to 1,000 times lower. This stark contrast highlights voids' role as an integral part of the cosmic web. They not only help us better understand matter distribution, but also play a crucial role in studying the interactions between matter and dark energy, two elements that dictate the universe's evolution. Voids challenge the notion of the universe as a homogeneous entity. Instead, they reveal a universe divided into distinct regions, areas of dense matter concentration and areas where matter is almost non-existent. This contrast paints a vivid picture of a dynamic and evolving universe, where voids stand as symbols of isolation, but simultaneously serve as evidence of how the universe expands and organizes itself. Furthermore, studying voids allows scientists to test the accuracy of cosmological models, particularly those concerning dark energy, as these regions provide a unique environment free from the disturbances of dense structures. The concept of voids highlights the diversity of the universe while posing profound questions about the origins and structure of space. These empty regions act as natural laboratories, where scientists can test theories about gravity, dark matter, and dark energy under minimal interaction conditions. From this perspective, voids are not merely empty spaces, but vital keys to unlocking the universe's greatest mysteries. One of the most astonishing features of voids is their immense scale, surpassing human imagination. These nearly empty regions of space exemplify the asymmetry in how matter is distributed across the cosmos, making them the largest and most enigmatic structures in modern cosmology. The diverse sizes of voids are one of their most striking attributes. Voids differ not only in shape, but also in size, ranging from small regions with diameters of a few million light-years to vast expanses stretching hundreds of millions of light-years. To put this into perspective, if the solar system were placed at the center of a large void, light from the nearest galaxies would take millions of years to reach it. In such a scenario, an observer would be surrounded by almost complete darkness, as light from celestial objects would be too faint or distant to detect. This scale emphasizes the stark contrast between the vastness of voids and the densely packed regions of the universe, such as galaxy clusters and superclusters. A prime example of the immense scale of voids is the Boötes Void, one of the largest voids ever discovered. Located approximately 700 million light-years from Earth, the Boötes Void has an estimated diameter of about 330 million light-years, large enough to contain our entire local galaxy cluster hundreds of times over. Remarkably, while a similarly sized region would typically contain thousands of galaxies, the Boötes Void hosts only about 60 known galaxies. This emptiness makes it resemble a cosmic abyss where matter has almost entirely vanished. The Boötes Void's peculiar nature has made it a fascinating subject of study, raising numerous questions about the mechanisms behind void formation and evolution. The puzzling emptiness of the Boötes Void challenges modern cosmological theories. One hypothesis suggests that this void may have formed through the merging of smaller voids over billions of years. According to this model, as nearby voids expand, gravitational forces from denser regions pull matter away from the empty areas, leading to the creation of colossal voids like the Boötes Void. However, some scientists propose that this unusual emptiness could be linked to poorly understood phenomena, such as the effects of dark energy or anomalies in the universe's early formation stages. The question of why such a vast region lacks matter remains unanswered, making the Boötes Void one of cosmology's greatest mysteries. Beyond the Boötes Void, all voids present significant challenges in explaining their formation and evolution. Standard cosmological models based on the cold dark matter theory, lambda CDM, have successfully predicted the existence of voids. Yet the extreme emptiness observed in cases like the Boötes Void remains inadequately explained. Studying voids not only enhances our understanding of matter distribution, but also allows scientists to test theories related to dark energy and the large-scale structure of the universe. The immense scale of voids is not only a testament to the universe's vastness, but also opens up a world of potential research. These spaces, with their colossal sizes and extremely low matter densities, raise questions about their origins while challenging scientists to explain the asymmetry in the universe's structure. From hypotheses about void mergers to bold ideas about the influence of dark energy, voids remain one of the most captivating and mysterious topics in cosmology. Voids, the vast and nearly empty regions of space, are not isolated entities but integral components of the cosmic web, a three-dimensional structure describing how matter is distributed on a large scale. This network not only highlights the universe's asymmetry, but also provides a comprehensive view of how elements like galaxies, gas, dust, and dark energy interact to form the universe's grand tapestry. The position of voids within the cosmic web is defined by the distribution of galactic filaments and superclusters. Galactic filaments are long, thin structures where most matter concentrates, forming pathways that connect massive galaxy clusters. Interspersed between these filaments are voids, enormous gaps spanning millions to hundreds of millions of light-years. If galactic filaments are the threads of a giant cosmic web, then voids are the spaces between those threads, They not only accentuate the stark contrast between regions of high and low density, but also shape the largest structures humanity has ever observed. Voids play a role in the cosmic web that goes beyond mere emptiness. They help maintain the overall balance of the network, influencing how matter aggregates in galactic filaments and superclusters. These empty regions reflect not just a lack of matter, but also provide a unique environment for studying the factors governing the universe, particularly dark energy, the force thought to drive the universe's accelerated expansion. Voids, with their lowest matter densities, offer an ideal setting for testing cosmological models, from dark matter distribution to the effects of dark energy on shaping the universe's structure. They are also places where physical phenomena can be observed in a nearly pure state, undisturbed by dense surrounding factors. The interconnection of voids adds another layer of complexity to the cosmic web. While considered empty regions, voids are not entirely isolated but often connect through tunnels or ultra-low density regions, forming a network of voids within the universe. These tunnels allow sparse matter to move between voids, creating a system of rarefied yet organized material distribution. The void network not only explains large-scale matter distribution, but also serves as a crucial tool for studying the universe's expansion. They provide valuable clues about how the universe has evolved from its early stages to the present. The existence and distribution of voids in the universe pose an intriguing paradox. While they represent emptiness, they reveal a highly complex structure and strong connections to other components of the cosmic web. Voids are not monotonous voids, but essential elements that shape the universe's overall picture. By studying them, scientists can better understand how matter accumulates in galactic filaments and clusters, and explore how dark energy influences the universe's evolution. The concept of voids emphasizes that even in vast emptiness, there is a degree of organization and order. These spaces, though desolate, prompt profound questions about the universe's origins and structure. They demonstrate how fundamental forces, gravity, dark energy, and dark matter, When imagining the universe, we often think of brightly glowing galaxies and massive superclusters. Yet, few realize that the vast empty spaces, voids, play a crucial role in shaping the structure and dynamics of the universe. How do these nearly empty regions influence the immense cosmic web that spans the universe? In the grand structure of the universe, voids and superclusters are opposing yet complementary elements that together create balance and order in the distribution of matter. On one side are regions of high-density concentration with thousands of galaxies, abundant gas, dust, and brilliant stars. On the other side are vast, nearly empty spaces. This coexistence gives rise to one of the most remarkable characteristics of the universe: diversity and complexity in its structure. Opposing but balanced, voids and superclusters collectively maintain the stability of matter density in space. Superclusters are bustling hubs of activity, where matter accumulates densely under powerful gravitational forces, attracting thousands of galaxies, stars, and intergalactic gas and dust. In contrast, voids are vast, nearly empty spaces where matter is so sparse that it is nearly non-existent. Without voids, the dense regions like superclusters would dominate the entirety of space, disrupting the natural balance of the universe. Voids are not merely pauses in the cosmic symphony of structures, but essential components that ensure the universe's diversity and stability in matter distribution. Within the vast cosmic web, Voids play an indispensable role, deeply interconnected with the cosmic web itself. This web is formed by galactic filaments, long, thin structures connecting galaxy clusters, and superclusters. Interwoven between these filaments are voids, resembling gaps in a colossal three-dimensional net. Voids not only highlight the contrast in density, but also serve as hinges, balancing gravitational forces and distributing matter. Their presence allows galactic filaments and superclusters to exist distinctly, maintaining the large-scale structure we observe today. Understanding voids' roles has become feasible thanks to modern cosmological simulations. Projects like Illustris and the Millennium Simulation have shown that voids are essential for sustaining the cosmic web's structure. In these simulations, when scientists removed voids from the models, matter no longer clustered into filaments, clusters, or superclusters, but instead spread evenly throughout space, resulting in a universe lacking order or complexity. This underscores that voids' existence enables the formation of galactic filaments and superclusters, highlighting their critical role in maintaining the universe's overall structure. Voids and superclusters are not just opposites by nature, but also complementary forces that together complete the picture of the universe's structure. Superclusters are radiant hubs where life and astronomical activity thrive, while voids are tranquil spaces where matter is sparse, and the laws of physics become more apparent. This combination not only emphasizes contrast, but also proves that both elements are necessary to create harmony in the universe. Studying voids and superclusters provides deeper insights into how matter is distributed and unlocks greater mysteries about how the universe operates and evolves over time. Although voids are nearly empty regions of space, they significantly influence how the universe expands and evolves over time. Characterized by extremely low matter density, voids are not merely passive gaps within the cosmic web, but play a crucial role in shaping the dynamics of space and the large-scale distribution of matter. Low density and weak gravitational forces are defining traits of voids. Containing minimal matter, including galaxies, gas, and interstellar dust, the gravitational forces within voids are too weak to attract substantial matter from surrounding regions. As a result, voids are tranquil zones in the universe, where the movement of matter is far slower than in bustling areas like superclusters. In galaxy clusters, strong gravitational forces drive collisions, mergers, and star formation, while in voids, the absence of such forces leads to a nearly static state. This makes voids isolated oases in the vast expanse, but also ideal environments to study how even weak gravitational forces influence the universe. Voids also play a vital role in the universe's expansion, helping to prolong and accelerate expansion in nearby regions. Without significant concentrations of galaxies, stars, or dense material to impede it, voids act as natural launch pads where space expands more freely. Research shows that the universe's expansion rate near voids is often faster than in areas with higher matter density. This is explained by the opposing effects of gravitational forces, which dominate regions of dense matter, and dark energy, which drives space's expansion. In voids, the lack of gravitational resistance allows dark energy to exert a stronger influence, accelerating expansion and shaping cosmic dynamics in ways scientists are just beginning to understand. Observational data from projects like the Sloan Digital Sky Survey, SDSS, provide clear evidence of voids' impact on surrounding objects. SDSS data reveal that galaxies near the edges of voids tend to be pushed outward faster than those embedded in clusters or superclusters. This demonstrates that even in the emptiest regions, voids significantly affect nearby matter through spatial expansion. Galaxies at the edges of voids often move in directions influenced by dark energy, further reinforcing voids' role in shaping the cosmic web and offering opportunities to study the interplay between dark energy and gravity in different environments. While the weak gravitational forces in voids might seem like a disadvantage, they actually make voids indispensable components of the universe's motion and evolution. The lack of matter in voids accentuates processes in denser regions, creating sharp contrasts between concentrated and sparse areas in the cosmic web. This not only helps maintain overall balance, but also offers a unique perspective on how dark energy interacts with matter in environments of varying density. Voids, with their serene appearance and weak gravitational pull, turn out to be critical components shaping the structure and dynamics of the universe. They are not merely gaps in space, but keys to better understanding the universe's expansion and how fundamental forces like gravity and dark energy interact to create the larger picture. These regions, while seemingly lifeless, tell compelling stories about balance and the evolution of the vast cosmos. Voids, though nearly empty regions, play a vital role in shaping and maintaining the universe's large-scale structure. They are not just gaps between galaxies, but pivotal elements in defining the boundaries between galaxy clusters and superclusters, while subtly connecting the components of the cosmic web in intricate ways. Defining the universe's structure is one of voids' fundamental roles. In the three-dimensional structure of the cosmic web, voids act as spatial cushions, separating galaxy clusters and superclusters into distinct entities. They are massive empty regions nestled between galactic filaments, long, thin structures where most of the universe's matter is concentrated. The presence of voids accentuates the contrast between high-density regions and nearly empty zones. For instance, if galactic filaments are the backbone of the cosmic web, then voids are the essential gaps that shape and reorganize matter distribution, providing a clear and ordered structure to the universe. While separating major structures, voids also play a crucial role in connecting them. Voids are not entirely isolated, but are often linked through low-density regions or bridges of tenuous matter. These connections, though sparse, act as pathways for ionized gas and intergalactic particles to move between galaxy clusters. These subtle links help maintain the continuity and order of the cosmic web. While voids create necessary separation between large structures, they also ensure the universe remains a unified entity, where components interact and connect seamlessly. This interaction not only shapes matter's distribution, but also opens up avenues for studying large-scale physical phenomena. The role of voids in studying dark energy has become one of modern cosmology's most critical areas. Dark energy, believed to be the primary driver of the universe's accelerating expansion, can be studied most effectively in voids due to their extremely low matter density. In environments nearly free from strong gravitational influences, dark energy's effects become more pronounced, allowing scientists to measure and better understand its nature. Recent studies using data from large galaxy surveys like the Sloan Digital Sky Survey, SDSS, show that the universe's expansion rate near voids is often higher than in regions with dense matter. This supports the hypothesis that dark energy dominates in areas less affected by gravity, making voids ideal natural laboratories for testing this theory. The connection between voids and the cosmic web reveals that even in seemingly absolute emptiness, there is profound complexity and interconnection. Voids are not passive gaps, but active participants in shaping, connecting, and sustaining the universe's structure. They demonstrate that in the vast cosmos, every element, dense or sparse, has its value and function, contributing to the overall harmony and balance. The presence and role of voids open new research horizons, bringing humanity closer to unraveling the universe's greatest mysteries. Amid the vast cosmic voids of the universe, regions known as voids that seem utterly empty, faint traces of matter persist. These remnants not only testify to the universe's formation history, but also unlock mysteries about how matter is distributed across immense expanses of space. How does matter exist in these cosmic wastelands? Voids are among the most remarkable regions in the universe, not because of their abundance of matter, but due to their extraordinarily low matter density. These cosmic deserts stand in stark contrast to dense galaxy clusters or superclusters, making them the most desolate regions humanity has ever known. This disparity not only shapes how we understand the universe's structure, but also opens doors to exploring unique physical phenomena. The near-absolute emptiness of voids highlights their distinct characteristics. While the universe's average matter density is already low, voids possess even less, approximately 1/10 of that average. In these regions, matter seems to disappear, leaving only a few isolated galaxies scattered across vast spaces. Unlike superclusters, where thousands of galaxies cluster in relatively small areas, voids are almost entirely devoid of galaxies, stars, or star clusters. Even intergalactic gas and dust, fundamental components of the universe, are sparsely present. This emptiness renders voids some of the loneliest expanses in the universe, underscoring the stark asymmetry in matter distribution. With their characteristic stillness, voids are not only devoid of matter, but also lack significant dynamical activity. There are no bright starlight, no powerful supernova explosions, and virtually no substantial interactions between celestial bodies. This creates an almost absolute silence, where cosmic activity has nearly ceased. The eerie tranquility of voids makes them ideal environments for studying the absence of matter and energy. Scientists have utilized these regions to test theories related to dark energy, gravity, and the large-scale evolution of the universe. Unlike dense areas with strong gravitational forces and complex astronomical phenomena, voids offer a purer view of fundamental physical laws, allowing scientists to delve deeper into the universe's mysteries. A striking example of voids' unique properties is the Boötes void, one of the largest known. Situated approximately 700 million light-years from Earth, Boötes void spans an estimated 330 million light-years in diameter, but contains only about 60 galaxies. For comparison, a similarly sized region in other parts of the universe would typically house thousands of galaxies. This staggering lack of matter raises numerous questions for scientists. How could such a vast expanse become so empty? Could its formation result from the merging of smaller voids? Or might it stem from unexplained factors in the universe's evolution? The absence of matter in voids not only sets them apart, but also plays a critical role in studying the universe's largest structures. These vast and tranquil regions help scientists explore how matter is distributed, how dark energy influences the universe's expansion, and the foundational principles shaping the universe from its earliest days. Voids are not merely empty spaces, but natural laboratories, where fundamental physical phenomena can be observed in the least disturbed environments. From their quiet emptiness, we learn how large and small elements in the universe interact to create the grand tapestry humanity is gradually uncovering. Voids, with their ultra-low matter density and stillness, are exceptional regions that illuminate many of the universe's great mysteries. They reveal the diversity in matter distribution, while emphasizing the critical role these empty regions play in understanding the universe's origins and evolution. Although voids are known as vast empty regions in the universe, they are not entirely hollow, but still contain traces of matter, primarily remnants from the universe's earliest epochs. The presence of these remnants sheds light on the formation history of voids and aids scientists in understanding the universe's evolution. Sparse ionized gas is the primary component of voids. These regions mostly contain hydrogen and helium, the first two elements formed after the Big Bang. However, their density is incredibly low, making up only a small fraction of the universe's average matter density. This gas is so thin that it cannot form stars or galaxies, but thanks to advanced telescopes like Hubble and Chandra, scientists can still detect its presence. Ionized gas in voids is often identified through absorption patterns of light from distant galaxies, creating fingerprints of elements from the universe's earliest stages. These discoveries provide valuable evidence of matter within voids and open new avenues to study how voids form and persist within the cosmic web. In addition to ionized gas, some voids also contain thin filaments, weak streams of ionized gas connecting them to nearby galaxies or galaxy clusters. These filaments, while difficult to observe, play a crucial role in maintaining connections between voids and the rest of the cosmic web. Like tiny blood vessels in a colossal body, these filaments transport matter and offer deeper insights into how the universe's various components interact and maintain unity. Though faint and elusive, their presence has been confirmed through cosmological simulations and observations, demonstrating that even in seemingly empty regions, connections to the broader universe persist. Observational evidence has been crucial in solidifying our understanding of residual matter within voids. Telescope surveys have recorded faint signals from ionized gas, confirming that voids are not entirely empty as they appear. A notable example is the discovery of faintly ionized hydrogen streams scattered across voids, identified through light absorption from distant galaxies. These findings not only illuminate voids' nature, but also offer insights into how remnants from the universe's early days are preserved and distributed within its large-scale structures. By studying these remnants, scientists can uncover key clues about the universe's formative and evolutionary phases. Although the matter within voids is minimal, its existence is immensely significant for understanding the universe's origins and structure. Voids, with their seemingly empty exteriors, are time capsules containing traces of a primordial universe where hydrogen and helium were the first elements created. These remnants help us reconstruct the universe's image shortly after the Big Bang, and play a vital role in answering major questions about how dark matter, dark energy, and gravity have shaped the current universe. Voids, the most desolate regions, hold secrets about the universe's ancient history. From faint ionized gas streams to delicate filaments, each component of voids contributes to the story of a vast universe where every element, small or expansive, plays a role in the grand design of space. Although voids are often perceived as entirely empty, detailed observations reveal that they are not completely uniform. Even in these vast, sparsely populated regions, faint celestial bodies and uneven matter distribution exist, offering new perspectives on how matter is organized in the universe. Small galaxies and dwarf galaxies are rare traces of matter found within voids. These are typically low-mass, faint galaxies with few stars. Unlike larger galaxies commonly found in clusters or superclusters, these dwarf galaxies exist in isolation, free from the strong interactions of neighboring galaxies. This isolation makes them dim beacons, solitary lights in vast spaces where matter is nearly absent. These galaxies, despite their modest size, hold significant scientific value, enabling astronomers to study conditions in the universe's least disturbed environments. uneven matter distribution within voids is one of their most intriguing features. Studies indicate that while voids appear empty on a large scale, closer observation reveals that matter is not entirely uniformly dispersed. Small galaxies, ionized gas, or filaments of matter often cluster at voids' edges, where they meet galactic filaments or denser structures like superclusters. These regions mark transition zones between the emptiness of voids and areas of high matter concentration. This clustering not only reflects how matter moves and organizes itself, but also highlights voids' role as boundaries within the cosmic web. The role of voids in cosmology is invaluable. Matter distribution within voids provides scientists with opportunities to test theories on the universe's formation and evolution on a grand scale. Cosmological simulations like Illustris and Millennium simulation have shown that galactic filaments and other large structures often develop along voids' edges. These edges, where small matter streams converge, act as nuclei for the formation of galaxy clusters and superclusters. This demonstrates that voids are not merely passive voids, but active participants in shaping the universe's structure. The uneven distribution within voids offers valuable insights into how the universe organizes matter. From isolated galaxies to faint gas streams, each element in voids contributes to the narrative of how matter coalesces into more complex structures. Furthermore, studying this distribution helps us better understand processes during the universe's early stages, from the formation of galactic filaments to the expansion of voids influenced by dark energy. Voids, with their simple and seemingly barren appearance, are rich with scientific data. The matter, though sparse, within them tells critical stories of the universe's evolution. The uneven distribution in voids not only illuminates how the universe's large-scale structures form, but also raises new questions about the roles of gravity, dark energy, and dark matter in shaping this immense expanse. From lone stars to delicate streams of matter, voids remain one of the key elements in unraveling the universe's mysteries. In the vast emptiness of the universe, the voids, there seems to be little of interest. Yet, the absence of matter in these regions provides critical clues to decoding how the universe was formed, expanded, and evolved. How do these empty spaces help us understand the cosmos better? Voids, the immense voids of space in the universe, are not merely empty regions, but serve as living records of how the universe has expanded and distributed matter over billions of years. By studying voids, scientists gain deeper insights into the universe's expansion process and uncover mechanisms for how matter forms and organizes across this vast expanse. The map of the universe's expansion can be visualized through the existence and growth of voids. These empty spaces serve as clear evidence of how the universe has continuously expanded since the Big Bang. As space expands, matter tends to be drawn toward denser regions, where gravity dominates, forming galactic filaments, clusters, and superclusters. Consequently, voids grow larger and emptier over time. These observations present a comprehensive picture of how the universe organizes matter, from tiny particles clustering into massive structures, leaving behind vast and expanding voids. Voids play a pivotal role in testing theories of cosmic expansion and dark energy, making them a focus of modern cosmology. Dark energy, the mysterious force believed to drive the universe's accelerating expansion, can be studied effectively through voids. Due to their extremely low matter density, voids create an ideal environment to observe the effects of dark energy without interference from strong gravitational forces in galaxies or clusters. Voids act as natural laboratories, where scientists can test hypotheses about how dark energy drives space expansion, while also refining cosmological models. The interaction between dark energy and matter at the edges of voids is particularly significant, as these are regions where the weak gravitational pull of voids meets the pronounced influence of dark energy, leading to faster rates of expansion. Empirical evidence from astronomical observations has strongly supported these theories. Large surveys, such as the Sloan Digital Sky Survey, SDSS, have shown that the universe expands faster in regions surrounding voids compared to denser areas like galaxy clusters or superclusters. This aligns with theoretical predictions about dark energy, providing additional evidence for its existence and its role in shaping the universe. By precisely measuring expansion rates within and around voids, scientists can verify and enhance their understanding of factors influencing cosmic evolution. Furthermore, the residual matter distribution within voids, from ionized gas to scattered dwarf galaxies, offers insights into how matter moved and concentrated in the early universe. Voids, seemingly simple and empty in appearance, carry critical narratives about how the universe formed and evolved. They are not merely passive gaps, but keys to unraveling larger mechanisms, from how dark energy drives expansion to how matter organizes into the cosmic web. Each void is part of the larger cosmic puzzle, where empty spaces and dense structures collectively form an ever-expanding and changing universe. Studying voids not only deepens our understanding of space expansion, but also provides opportunities to address profound questions about the universe's origins and ultimate fate. From vast emptiness to enigmatic borders, voids embody a universe of contrasts and complexities, where every component plays a role in shaping evolution across billions of years. To uncover the secrets hidden within voids, scientists have employed advanced tools and techniques, blending observational data with cosmological simulations. These methods not only decode the nature of voids, but also open new doors to studying the universe's structure and evolution. Optical and X-ray telescopes are critical tools for observing voids. Modern telescopes, such as the Hubble Space Telescope and Chandra X-ray Observatory, have been used to analyze light and matter within these regions. One common technique involves observing light from distant galaxies passing through voids, measuring its absorption and scattering by ionized gas and cosmic dust within the voids. This approach not only identifies the extremely low matter density inside, but also provides detailed information about the gas composition, primarily hydrogen and helium. Data collected from optical and X-ray telescopes have revealed varying degrees of emptiness in voids and how they interact with surrounding structures like galactic filaments or superclusters. Thanks to these telescopes, scientists have confirmed that voids are not entirely empty, but contain traces of matter left from the universe's early days. In addition to direct observation, cosmological simulations play an essential role in recreating how voids form and evolve over time. Large-scale projects like the Illustris project and Millennium simulation have used physical laws and empirical data to generate three-dimensional models of matter distribution in the universe. These simulations illustrate how matter is drawn to denser regions, leaving behind vast empty spaces known as voids. They also provide valuable insights into how dark energy influences cosmic expansion. By comparing these simulations with observational data, scientists can validate and refine cosmological theories, gaining a deeper understanding of voids' roles in the universe's large-scale structure. These simulations also allow predictions about how voids will expand and change over time, shaping future research directions. Emerging technologies are opening new possibilities for studying voids, especially in distant and hard-to-observe regions. Next-generation telescopes like the James Webb Space Telescope, JWST, are expected to collect more detailed data on voids, particularly in areas with extremely low matter density. With its infrared observation capabilities, JWST can detect faint traces of ionized gas or scattered dwarf galaxies within voids. Additionally, upcoming telescopes such as the Giant Magellan Telescope, GMT, and Square Kilometre Array, SKA, promise higher resolution and sensitivity, enabling deeper observations into voids and studying them on an unprecedented scale. These advancements will not only expand the scope of research, but also enhance the accuracy of cosmological models, helping scientists better understand voids' roles in the universe's grand design. Through a combination of direct observations and advanced simulations, voids have shifted from being dark regions of ignorance to becoming valuable sources of information about how the universe formed, expanded, and evolved over time. These studies not only decode the universe's large-scale structure, but also bring us closer to answering questions about dark energy, dark matter, and the fundamental forces shaping the cosmos. Voids, once perceived as simple, empty spaces, now reveal complex and intriguing stories about the universe's motion and dynamics. Research on voids not only deepens our understanding of matter distribution in the universe, but also opens new doors to exploring phenomena and principles governing the cosmos. These vast spaces are not merely forgotten parts of the universe's structure, but hold the keys to deciphering the most significant theories in cosmology and shaping future research directions. Supporting the Big Bang Theory is one of voids' most crucial contributions to science. According to this theory, after the Big Bang, matter in the universe was initially evenly distributed but unstable. Over millions of years, gravitational forces caused matter to coalesce into clusters, galactic filaments, and superclusters, while less dense regions expanded into voids. Observations of today's voids align perfectly with predictions from Big Bang-based simulations, providing strong evidence that not only reinforces the theory, but also illustrates how matter has organized and distributed itself in space since the universe's infancy. Voids serve as living fossils, recording how matter moved and concentrated, directly reflecting the formation and evolution history of the cosmos. Voids are also natural laboratories for studying dark energy. Believed to be the primary driver behind the universe's accelerating expansion, dark energy is best examined within voids. In these empty regions, the lack of matter eliminates confounding factors, allowing scientists to accurately observe how dark energy influences space. Studies reveal that near the edges of voids, where gravitational influence diminishes, the rate of space expansion increases, precisely as predicted by dark energy theories. By analyzing data from voids, scientists have gathered compelling evidence for dark energy's existence and its dominant role, one of the greatest and most challenging questions in modern astrophysics. These findings not only bolster cosmological models, but also broaden our understanding of this enigmatic force. Guiding future research, voids are indispensable for developing new models and theories on how matter and energy interact in space. Understanding how voids form and evolve helps answer profound questions about the universe's origins and structure, while opening avenues for future exploration. Data collected from voids can refine cosmological simulations, test hypotheses related to dark energy, dark matter, and gravity, and serve as a foundation for developing advanced observational technologies. From next-generation telescopes to sophisticated data analysis tools, these studies pave the way for extending humanity's vision into the farthest reaches of the universe. The scientific significance of voids transcends their empty nature. They are unique windows into the universe's essence, where each empty space contains rich narratives about origin, evolution, and the forces governing the cosmos. Through the synergy of direct observations and advanced simulations, voids not only illuminate the universe's past, but also shape how humanity explores and interacts with its greatest mysteries in cosmology.